Hello everyone, my name is Devendra Kapadia and I'm the manager of mathematical computation at Wolfram. It is a great pleasure to speak to you about what's new in mathematical computation today. Now, mathematical computation is a fairly big area of the Wolfram language and it includes both symbolic and numerical computation. And my goal for today's talk is to give you a broad overview of what's happened in this area during the last year or so. So let me begin with the plan for my talk. So I would like to discuss new developments related to a few areas. The first one is algebra, and here we have non-commutative algebra, which was started in 14.3, and now we have some special non-commutative algebras coming up in the new release 15.0. We also have a function called partial fractions, which I hope will be of value to students who study calculus or faculty who teach calculus, etc. And then the next theme for the talk would be matrix computation, where we have some nice advances, some new functions, some performance improvements, and this is an active area for the team right now. Historically, for the last few decades, we have focused on hypergeometric special functions mostly, and in particular the Gauss hypergeometric function, the Meiji function, etc. And of course, we'll continue with those functions, if you like, forever. But in this release, we're going to try out uh, a new family of functions related to the Riemann zeta function, multivariate versions of Riemann zeta and other functions. So this development is motivated by Feynman integral calculus, and it's pretty modern in spirit, so I hope you'll enjoy it. Coming to calculus, we have uh, two new things. One is an experimental approach using neural networks to solve symbolic differential equations, which has turned out to be quite successful. I'll talk to you about it, and I think that it's encouraging we can use this very modern technology in our system. And on the other hand, we have the discrete Hilbert transform in version 15, which is the discrete counterpart of the symbolic Hilbert transform, which we had in version 14.3. Now, of all the things that we do, perhaps the most applied area is PD modeling, and here we have some new developments for fluid flow, non-Cartesian coordinates, etc. And I'll take up one example just to give you a flavor of what's happening over here. As a team, we always strive to improve our documentation in various ways. So for the upcoming release, we'll have improved documentation for special functions, in particular detailed sections, and there are also a couple of nice monographs to talk about. Now, most of us in the team are, teachers or have been teachers at some point in our careers, and so for us, teaching courses and writing books is a very natural activity. So I'll talk about a couple of new Wolfram U courses and some Wolfram Media books that we have been working on during the last year. So with that plan understood, let's begin with the first theme, which is non-commutative algebra. So version 14.3 includes support for basic operations in non-commutative algebra. So for example, here's a non-commutative expand. You have a plus b, the whole square. That's a kind of generalized power. And the answer turns out to be a square plus b square. And then you have an a times b and a b times a, because you can't really do twice a times b. There's no commutative over here. But in practice, what happens is that often this kind of pair will shrink to something like -1 or something like that. And in that case, the question is, what do you do? Well, in that case, what we have is algebras with relations, and that's what version 15.0 will support. And it turns out that this idea of relations is very important for several new named special algebras in the system. So we'll have Clifford algebra, which comes up in connection with spinors and quantum theory, etc. The Grassmann algebra, which is associated with the exterior calculus and exterior algebra, and the Weil algebra, which is quite useful for differential equations. So as just a single example for these, let me take up a particular Clifford algebra. So here I'm going to define the Clifford algebra 1, 3, and you might wonder what the 1 and 3 mean. Well, here's the 1, the gamma naught, and the 3 over there. And the reason why they're grouped this way is that when you take the product, the non-competitive product of these over here, then the first one gives you a 1 and the remaining three give you a -1. So 1, 3 means 1 plus sign, 3 minus sign. And if you are a physicist, you'll immediately recognize this as something to do with Minkowski space. And of course, that's true. In fact, what you can do now is to use these gammas to define a time-like positive Minkowski matrix. A time-like means that you got a +1 over here for the time, and then the negative signs over there. And then you can verify several popular identities. Like here's an example of something that gives you a 4. And the question is, why did I call this Clifford algebra Dirac? Well, the answer is that this algebra, the Clifford algebra, can represent using so-called Dirac gamma matrices. And in turn, these gamma matrices appear in the famous Dirac equation. So you see the gamma over here. So the Dirac equation is probably the most beautiful equation in modern mathematical physics, and that's where the gamma matrices occur. So with this new functionality, we are now entering into a slightly more advanced level of, if you like, quantum theory. Okay, so with that, let me go on to the college calculus theme for today, which is partial fractions. So we have a new function called partial fractions, which will compute partial fraction decomposition 15.0. And so for example, here's a rational function, and I've left the denominator factored just to make things clear. So you want to partial fraction of the rational function, and what you get back is a kind of polynomial part and a fractional part over here. And what the new function can do for you is actually it can not just give you the answer over here, but it can also find the individual parts, the polynomial part like over here, and the fractional part like over there. And you might wonder, why did we not use apart for this purpose? Well, apart is a very old function. It's used in lots of places, and messing around with it didn't look like a good idea. And aside from that, partial fractions will do a kind of complete decomposition with complex numbers all the way out. Apart will stop short of that, and of course we have an extension option to go back and forth between those two possibilities. But I think partial fractions should be something that might be useful to a lot of people who work with this kind of algebra. Okay, so on to a matrix computation, and here we have around 15 newer updated functions of matrix computation in the new release. And I'll just take a couple of examples over here. So let's talk about the Bunch-Kaufman decomposition of a symmetric matrix. So here's a matrix, pretty large size, 500 by 500. You symmetrize it, feed it to the new function, and what you'll get back quite quickly, actually, in the new release is a decomposition which has got a lower triangular matrix, a block diagonal matrix, and a permutation matrix. And this really is state of the art. It's very efficient and should help people who work in numerical linear algebra. We also have some nice improvements, performance improvements, other improvements. So here's an improvement for matrix function. So that's a matrix, and the matrix function in this case had a leaf count of around 2.5 billion, give or take a billion in 14.3. And now it comes back quickly, and the leaf count is, as you can see, much, much smaller. So matrix computation looks like a good area to keep working in, and we'll keep on working on dense matrices as well as sparse matrices in the future. We have a new library which we've been looking at, a MUMS library, which has proved useful for our 3D modeling functionality, and we'd like to now explore sparse matrices once again in the Wolfram language. Okay, so on to special functions. So we'll talk about the multiple zeta under 8 functions, but let me just recall that the Riemann zeta function has been around forever, since version 1.0, and this function is defined by an infinite sum. So it's sum from 1 to infinity of 1 over n raised to s. S is the parameter over here, and I've put generation condition goes true, so we get back the concurrence condition, which is that the real part of s should be greater than 1. Now, this function has many special values which are known. So for example, the even values, zeta 2, zeta 4, etc., are known in terms of pi, but unfortunately the odd values are much harder to work with, so they stay unvaried over here. And on the negative side, zeta of -1, if you put -1 over here, you in fact get the sum of the natural numbers. And of course, you know from YouTube, if not anywhere else, that that sum is -1 over 12. So that's the story as a 14.3. In version 15.0, we have the multiple zeta function as well as many other functions related to polylog and harmonic number. Okay, so that's a big area. So I'll just take a few examples for multiple zeta itself. So multiple zeta is defined by a multiple or an iterated sum actually. And you can see where you got 6, 8, 2, 3. That gives a multiple zeta 6, 8, 2, 3. And like the zeta function, many special values are known. You might even recognize from the earlier slide that the zeta 3 and zeta 5 are staying unevaluated over here, and the pi's come from obviously the even zetas. And in fact, these sums satisfy a so-called quasi-shuffle algebra, and so you can descend down and get expressions in terms of kind of the lower values of multiple zeta and zeta. That's a vast area. People might have spent like almost a lifetime if you look at grad students and professors together. And what we've done is to just kind of scratch the surface of this beautiful but vast area. And I remember a long time ago, for version 7, I worked on Euler sums using contour integration methods. But now with the new multiple zeta at hand, we have many new beautiful Euler sums available in the current release. I should warn you that this functionality is still in development and the design might change. So you might not exactly see the same things in the final release, but this is where we are right now. And you might ask the question, what was the motivation? Well, one is the number theory, the classical motivation for the zeta function, the Riemann zeta function, the Riemann hypothesis, etc. And then particle physics, a more modern endeavor for the last 60 years, maybe, starting with Richard Feynman. And I think that that's where all the expertise is right now mostly. So we have tried to make contact with them while recognizing that that is a vast area in which we have some of our best users working. Okay, so on to calculus and neural networks. So to cut a long story short, DSolve includes the neural network method for ODs in 15.0. And this method gives new or improved solutions. Sometimes you might get a solution which didn't happen at all in an early release, or you might get an improved solution for many first order ODs. That's the class we are focused on right now. So here's an OD that's pretty messy, probably not a homework problem for anyone. And if you were to try it in 14.3, this is what you'd get. Not particularly pleasant. It's a long, long solution. But this very example gives a beautifully simple answer using neural networks in the new release. I think that's really elegant. And of course, we know from Penlevet's work that as you change the arbitrary constant, the branch cut structure of the solution might change. But I just picked one value of C1 to plot this complex plot of the solution. It's quite nice and to look at. Well, it looks nice. Question is it correct? And that's, of course, the catch with using neural networks, that they have what are sometimes politely called hallucinations. So what we do is internally, once we decide we want to return the neural network solution, we actually use one of our simplifiers to check that it in fact is correct. So we have a like a more or less certain solver from an uncertain method. And given the success of this, it looks like we might even try and apply this to other problem symbolics. If you have any suggestions, do let us know. We'll be happy to hear them. Okay, so the other calculus improvement is Hilbert transform. So in version 14.3, we introduced Hilbert transform, the symbolic Hilbert transform, which applies a 90-degree phase shift to a signal. So if you take the Hilbert transform of sine, you get a negative cosine. And so here is a pair of functions, sine, cosine, you see a shift by pi over 2. And what the new function does in 15.0 is it'll work with data. So here's some kind of random data similar to the earlier one. And then again, we do the same thing and you see the shift over here, but now with data. And the reason for introducing this new function is that it has many practical applications to medicine, seismology, all kinds of things. So I think the documentation for this should be quite beautiful. Do look at it when the release happens. Okay, now I go on to PD modeling, where we have several new features, support for non-Cartesian coordinates and so-called swirl flows, like, got a beaker and a mixer inside, and then you swirl it around. Maybe something like a tornado. If you live in this part of the US, you probably know tornadoes quite well. Um, so that's an example where you're seeing a cross-section of beaker with that mixer over here. You can set up the problem, you can solve the problem for velocity, and you can visualize the magnitude, and it's all quite pretty, I think, the whole area of fluid dynamics. So we have a nice improvement for PD modeling over here, and of course, this is an area that's going to flourish for a long time to come. Okay, so on to documentation. So special functions documentation has been a focus for a long time. We've added examples to almost every part of those pages, but what was remaining was the top detailed sections, and there we have drawn on a few resources like the functions website, MathWorld, etc. And we're trying to update 100 out of the roughly 300 functions that we have for 15.0. You can see an image over here of one of these updated functions, the Bessel function. And then we also have on the PD modeling side a nice monograph on plasticity, which is a pretty advanced topic, but this monograph does a good job of trying to make it kind of computable in the Wolfram language. And I should just mention that we are lucky to have a nice blog post on boiling an egg as an introduction to a PD modeling functionality, suggested by late Michael Trott. So with the help of the Wolfram Alpha team, we managed to put together this nice blog post, and we're getting good feedback for it. So documentation continues to be a good focus for us. And then, of course, for a long time, we've been working Wolfram U courses. We have things starting from elementary algebra, calculus, linear algebra. We have lots of courses, and recently, a course on special functions went live. That's an area where we really have like expertise and very unique functionality. I think that course is going to be of great value to people who work in the field and people who work in physics, etc. The other course that's going live soon is one on PDs. Now, this is a beautiful area, very applied, and in fact, the course includes examples from engineering and physics and finance and all kinds of things, and I think it should be an excellent course. So we're always working on new courses before the old ones are kind of done. So right now we're working on a game theory course and a symbolic computation course. The game theory is more for, let's say, economists, and the symbolic computation course is for everyone because we are a symbolic computation software historically. Today, of course, much more, but that's where the Wolfram language began. And finally, I'd like to talk about our book endeavors. So this is, of course, something that's going on in several teams in R&D, but we're hoping to publish a book on complex analysis very soon based on the course in Wolfram U, and then a book on Laplace transforms. Those two are very closely related, of course, but I think they'll be a nice computational approach to these topics. And if just in case you like these covers, well, they're mostly done with the Wolfram language with help from our excellent design team and experts. So I think that they'll be appreciated by our users and people who are trying to understand both the Wolfram language and a theme in mathematics. Future topics will include probability, linear algebra, etc. This stream is going to go on for some time. We'll probably have, if you're really lucky, in the next couple of years, probably 10, 12, 15 books in this series. So with that, I'm ready to conclude my talk, and thank you all for being here, for providing the right encouragement and support that we need to go on, to all the team members who are always working so hard, to other teams in R&D and the company who cooperate with us to produce all these beautiful new things. And I do hope that you will have some questions for me. I'll stop over here, but it was a great pleasure to talk. And for me, it's time to reflect once the conference over and then move on to the next batch of development projects. So thank you very much.
Okay, so I think I'm quite pleased with what's happened in our area for this release for 15.0, and I hope you could get some flavor for it. I could barely cover a lot of what we had in this release, but I hope that you'll take the time to attend other talks, which, well, some of them happened early on, the PD modeling and special functions, and then we'll have many more talks today. There's a talk by on neural networks and differential equations by Aram and Syria. There's going to be another talk by Adam Strasbonsky on non-commutative algebra. Another talk by Dan Lichtblau on the matrix computation stuff. Then we have an office hour. You can come and talk to us. And then we finally will have a workshop on typesetting, which I think is something that everyone should learn, including myself. I think this is a very important part of this. So do take advantage of what we have today, and let us know how you like things. I see a couple of questions from Nick. Speaking of Feynman, what about divergent integrals? Well, the current integrate has got. I shouldn't give away internal things. Okay, maybe I regret it. But when you said generate conditions goes to false in the current integrate, it does some kind of Hadamard regularization. But now that you've asked, we do plan to have specialized support for Cauchy and Hadamard integration in the near future, and also more divergent integrals in general. It's a strange thing that we have divergent sums were covered in version 7, but then we have kind of not got back to divergent integrals. I do have some kind of prototypes. It's a vast area. Let's say this way, we might get to it in the next year or two and have a function which actually, first of all, checks convergence, and then to have ways of computing divergent integral. But thank you, Nick. I do understand those are important. We just don't have a good handle on them or a good way to deal with them without being kind of careless. But thank you. The other one, are quaternions implemented in the current version of Mathematica? Well, there's a quaternion package, if that's what you're referring to, and maybe there are other people in the audience. If Adam or someone happens to be here, they're welcome to reply to this. But I think the thing is that for quaternions, we'd like to do a better job. So I guess we have a little bit, but basically the new Clifford algebra has quaternions as a special case. And so thank you for that. I think we'll just go ahead and do it at some point, Bogdan. Okay. Any other questions, comments, what do you think we should do on that? We have a few minutes more now, and I'll be happy to answer them. Let me check the chat in the meanwhile. Thank you, Jilakro. I do think it's nice to have an audience that actually, and there are lots of people over here who are real experts, so if you have any comments, suggestions, we'll go ahead. We have another talk in around 7 minutes, so we shouldn't go on for too long, but I guess a question or two more would not so go ahead. If you have anything to say, you can do it, as I will close the talk in a couple of minutes.
Hi, Devendra. You have one more question in the chat section.
Oh, really? Okay.
Yes.
Okay. So it's turbulence. Oh, Zbigniew, nice to see you. Well, that I think should meet Oliver at some point. Message him, but we have, let's say, got approval in some sense to do turbulence. It's just a question of finding the time to do it. I think in a year more. But if I know that you are an expert in engineering, and if you think it's important, I guess that's even more. So I'm a mathematician. I don't look at turbulence the same as I've got some vague notion. It looks like turbulence in engineering is a much more concrete thing with all kinds of special models. So yes, we're giving some thought. Oliver Rubin-Koenig is the expert over here, he and Martin. I think we should see it in the next year and a half. I know you might be disappointed, but it's one thing we have backed off because we just want to do things right. But that's a great suggestion. So then, thank you very much, everyone, and see you at the next talk.